You know, for decades, our computers have been getting exponentially faster, all thanks to one simple rule: just cram more transistors onto a chip. But what if that whole roadmap is about to hit a brick wall? Okay, let's dive into a totally new kind of chip tech that doesn't just squeeze more in, but actually changes the way a computer thinks.
Take a look at this number, 10 to the 15th. That's a 1 with 15 zeros after it, a quadrillion. According to research in Nature Electronics, this is the kind of mind-boggling information density per square centimeter that our chips are getting close to. It's an incredible achievement, all thanks to that relentless trend we call Moore's Law.
And that leads us to the big question. While we've been chasing all this performance, there's been a massive side effect: power. Our most advanced chips are hitting a power density wall. They're getting so dense and so power-hungry that it's just becoming unsustainable.
So this whole problem, it's got a name: the binary bottleneck. For over half a century, computers have spoken a very simple language: on or off, 1 or 0. And this binary system, running on what's called CMOS technology, has worked wonders. But like we're seeing, just jamming more of these binary switches together isn't working anymore. It's creating a massive energy traffic jam.
So what's the alternative? Well, instead of just on or off, what if we added a third option? Think about a normal light switch. That's binary. It's on or it's off. Now think about a three-way lamp: off, low, and high. That's the basic idea behind ternary logic. By having that middle state, you can represent way more information with fewer parts, which makes the whole system a lot more efficient.
So where do we even look for inspiration on how to build a more efficient computer? Well, it turns out the best example is the one you're using right now to process my voice: your own brain.
That's right. The human brain runs circles around our best supercomputers, and it does it all on just 20 watts of power. That's less than a dim light bulb. And one of its big secrets? The brain uses a kind of ternary processing. It's proof that thinking in threes is an incredibly energy-efficient way to operate. And look, this isn't just some wacky thought experiment. Researchers are taking this very seriously. As you can see from this quote, the scientific community sees a shift to ternary as pretty much the most direct way to smash through that power bottleneck we're stuck in. So the big question is, how do you actually build one?
Okay, this is where it gets really cool. Say hello to Ternary CMOS, or T-CMOS for short. Now, instead of trying to invent some crazy new transistor from scratch, researchers found an amazing way to teach an old chip a new trick, using a little help from the weird world of quantum mechanics.
The secret ingredient here is a wild quantum effect called band-to-band tunneling. See, in a normal chip, any current that leaks out is a bad thing. It's just wasted energy. But with T-CMOS, they took that predictable little quantum leak and turned it from a bug into a feature that creates a stable, consistent, and all-important third state. And the beauty of this is how elegant it is. You literally start with a standard chip design. Then, using the same factory tools we have today, you create this special little tunnel junction. That one tweak lets the quantum tunneling happen, creating that tiny current. And just like that, boom, a regular old binary transistor now has 3 distinct states: off, a new middle state, and on. Okay, so a clever idea on paper is one thing, but can you actually build it? And more importantly, can you build millions of them? That's the real test that separates a cool experiment from a true revolution. And the answer is a huge, resounding yes. The researchers proved they could build these T-CMOS devices on standard silicon wafers, using the exact same commercial factory processes that make the chips in our phones right now. This is absolutely critical, because it means T-CMOS isn't some futuristic fantasy. It's compatible with the billions of dollars of infrastructure we already have.
So just how much more efficient are we talking? Well, the numbers are kind of staggering. A T-CMOS chip doesn't just need less power because it's ternary. It can also run at a much lower voltage. When you put it all together, they project it could be over 400 times more power efficient. That's not just an improvement, that's a complete game changer.
But is it stable? I mean, if that middle state is all wobbly and unreliable, the whole thing is useless, right? Well, get this. Across an entire wafer, with all the tiny little variations that happen in manufacturing, that crucial third state only deviated by 16 millivolts. That is rock-solid stable, proving the design is tough enough for the real world.
All right, so we've got this revolutionary new chip tech. It's crazy efficient. You can actually mass produce it, and it's reliable.
So what? What does a future running on 3 states actually look like for us?
Well, the potential is just massive. We could build brain-like AI systems that are way more powerful and efficient. Imagine all those tiny, smart sensors for the Internet of Things running for years on a single coin battery. Your smartwatch could finally last for weeks on a charge instead of, a day and a half. And for memory, you could cram 50% more data into the exact same physical space.
The ultimate goal, as the researchers themselves say, might not be to completely replace binary. Instead, it's about creating a powerful hybrid future. Imagine systems that use ultra-efficient ternary parts for things like AI, working side by side with speedy binary parts for traditional computing, all seamlessly integrated on one chip.
For half a century, our entire digital world has been built on a foundation of just ones and zeros. But it turns out, this clever quantum trick, which was hiding in plain sight in the silicon we already use, might just unlock the next era of computing. It really makes you wonder, right? Will the next big revolution be calculated in threes,